Morning, my fabulous chemistry minions. Organic video number 9. This is it, the last one. Hallelujah. Organic reactions. Sorry they've been so long. There are 7 reactions. Let's get right to them. I'm going to get into 6 of them with some detail. First one, combustion. You read all that stuff because I know you know how to read. What it's going to be is any hydrocarbon with oxygen as a reactant, because we need oxygen for fire, right? Will produce always carbon dioxide and water. Make sure somebody reminds me to do this for you, please, and prove that it creates carbon dioxide and water. Let me give you a quick example of what we're talking about. So you pick the hydrocarbon. The more complicated the hydrocarbon, the harder it is to balance these things, but balancing combustion reactions is something I like to do. I'm not going to lie. Oxygen has got to be present, so that's one of the keys. Can't have fire without oxygen, so that's one of the things. You might want to start that. You're looking for that. And then you're always going to get carbon dioxide, and water is the only products. So here is an unbalanced example of a combustion reaction. You probably want to start the last 3 things. You need oxygen as a reactant, you need carbon dioxide, and water as the only products. And that is a combustion reaction. You see those 3 things. Wham, there you go. Okay. Addition reaction. We need to be able to differentiate between an addition reaction and a substitution reaction. You're going to find in an addition reaction that there has to be a double or a triple bond, so I can just add the halide in. So it's got to be an ene or an ine. It's got to have a double or a triple bond, so we know that. I just told you. And then there's going to be some halogens, so like Cl2, Br2, F2, somebody in group 17 generally. And it's going to make this straight up halocarbon with one product. And you notice that's up there too in the reading. So let me give you a quick example. Here's my alkene. That follows the CnH2n. So it's an alkene, not an alkyne. Okay, there will only be 2 hydrogens if it was an alkyne. I'm going to put Br2 into this particular equation. So there's my halogen. And I'm going to literally just break that double bond, add the BRs in, and here's a picture of what is actually going on. And yes, in this box, I would draw this reaction. This part in the bottom, though, where you see the actual two carbons is F, where you see the ethene molecule, it goes ethene plus Br2, then the arrow. And you notice that the double bond is then broken, and the BRs are starting to go into the parking spots that just opened up where I could have fit H's, and then I get this one product. And I don't really care if you draw the BRs up and down, top to top, bottom, bottom, on the ends. I really don't care where you draw the BRs, but specifically the BRs need to be 1 on each carbon. That is part of the deal, because as I open it up, each carbon forms 4 bonds. Then you wouldn't find all of the H's on one carbon and 2 BRs on the other. But where on the carbons you put them, I really don't. It's all the same thing. Okay. Now substitution is quite similar, except for now I'm going to have an alkane that is satiated. So because I can't just create parking spots, one of the halides are going to switch in for one of the hydrogens, and then the hydrogen is going to come out, and that's going to end up with, now you see 2 products, and one of them is going to be an acid because it's going to have a hydrogen and a fluorine, or a hydrogen and a chlorine, or a hydrogen and a bromine, and all those are acids. Okay, so I'm going to have 2 products, one of them being an acid. So I'm going to need an alkane. I need a single bonded hydrocarbon, so I called it an alkane. I need that halogen again, so another diatomic group 17 guy. And then I'm going to make this thing called a halocarbon, which we learned in the last one, and an acid, because that H is switching out. So an example is now C2H6 is an alkane single bonded. I'm going to add bromine into it again so you can see what happens now. And then I'm going to make this, notice there's only 1 bromine in there instead of 2 like in the last one. And I'm going to make HBr, hydrobromic acid. Okay, and here's a picture that, yes, you do need to draw. And you see I have this 3-dimensional methane. So this doesn't work perfect to our thing, and I'm moving Cl. If you want to put BRs there, I'm okay with that. But notice the Cl-Cl splits. One Cl replaces a hydrogen, the other hydrogen goes over with the Cl. Okay. Sorry, though, those 2 things don't perfectly match, but that was the picture I found that was the best, and I didn't make the change of the top. I don't know, maybe I did it differently last year, but wasn't thinking it clearly. Esterification makes esters. This is a dehydration synthesis, which is kind of neat. I'm going to take an organic acid, which is a functional group piece that we learned last video, and an alcohol, which is something we learned last video, and I'm going to pull out water, and when I do that, I'm going to make an ester. Okay, so a quick example of what we're talking about. Here's my coup. Okay, ethanoic acid. I'm going to combine that with 2 carbons as with ethanol, and I'm going to make this ester and water. And you need a picture to see what's going on. And here comes the picture. And you can see in the blue, the H is going to come off the alcohol, the OH is going to come off the carboxylic acid, and that's a carboxylic acid is just any, it's a short code word for a coup, for an organic acid. It's a generic name. That's going to lose the OH, and notice that HOH is going to form the water. That's why we call it dehydration synthesis. I synthesize those two things, so where the waters come off, those two things come together, and that's where the C and the inline O come together. Okay, good. That is an esterification. You just need to know that esterifications make esters, and if you can remember that it's a dehydration synthesis, that's great. We're moving right along. Saponification. I do not know how you figure this out, but it's making soap. Number 1 rule of Fight Club is we don't talk about Fight Club. This is where I'm going to take an ester and I'm going to hit it with a base, preferably a strong base like lye, like really strong, like burn your arm off strong. And that's going to produce soap and glycerol. Okay, glycerol goes. All right. Fermentation, one of my other favorites. This is making alcohol. You need to know that fermentation makes alcohol. So if I take sugar and hit it with an enzyme, I will make alcohol and carbon dioxide. Cool. So here's sugar, glucose. We need ourselves an enzyme. And then I can make from that alcohol, and this is an ethanol with carbon dioxide. And ooh, this one I balanced. Okay. So fermentation, you need to know, makes alcohol. Moving right along, last one, there's no real notes on this. This is a polymerization. If you can fit it in there somewhere, what all this means is that if I have a monomer, which is a one little guy, and I see that in parentheses, if I link them all together, same guys, I can link them together 15 long, I can link them together 30 long, I can link them together 60 long. Generally, how I control that is with temperature and time. And I know where to stop that when I get good at the reaction. This is something Kodak was phenomenal at. I link together a bunch of monomers, which are the exact same things, and I can make a polymer. That's where we get this word polymerization. Poly means many. Link them all together, and we did that, and that's at the bulk of. I do see this one sometimes as a question, I'm not going to lie, but I don't know how else to talk to you about it except for it's linking a bunch of little ones together, and honestly, there's no limit. I could make 400 monomers long of one molecule. So there's that bit of flexibility, you could say, with this. The other ones don't have as much flexibility because I make specific molecules. This makes any number of kinds of molecules because I can make those chains as long as I really want. Okay, and with that, I think we are done for the unit. Good job. You guys are working hard. I'm really proud of you.